Okay, thank you very much. Really happy to talk to you today about geological evidence for the history of Venus's atmosphere. And it's a complex issue, very complex issue. We're excited to think about a lot of these things and come up with some preliminary conclusions that might lead to more research and also a lot of the measurements that we're going to make in the upcoming Armada of Venus missions. Next slide, please. So a critical question here is that, I've been around a while, and these questions have perplexed planetary sciences since really the early part of the space age. And I was just a toddler then, of course. But the key here is, what's the origin of the currently observed Venus runaway greenhouse atmosphere? And why is it so different than that of the Earth? This is really critical. Everybody knows this. But what's its relationship to the observed, now that we have Magellan data and Venera 1516 data, what's its relationship to the observed, less than a gigayear, Venus geological and geodynamic history, circled in red there, on the left? And then what's its relationship to the cryptic or hidden part, greater than a gigayear, pre-Fortunian Venus geological geodynamic history? That's the majority, like 80% of the history of the planet. Next, please. So what we're trying to do, of course, a lot of people have done significant forward modeling. Let's take the origin of the atmosphere from the beginning and look at its evolution as a function of time, assuming a bunch of different, very reasonable assumptions, Bullock and Grunspoon and others. Take a look at volatiles that are derived from the interior and also from space. And what's their influence on the evolving atmosphere? We heard a presentation just a few minutes ago on trying to calculate and figure that out from a model point of view. What's the interaction with the surface, and what's the rates of loss of space? And then the end product, of course, is indeed the current atmosphere. Next, please. So a number of forward models, really exciting, okay? I mean, there's been a lot of development this recently, particularly most recently by the Wei et al. And Wei Del Genio papers. Basically, there are more Earth-like climate conditions are predicted in the early history. You can see the red arrow there in the upper left and the lower right. And these may have actually had oceans and nitrogen-dominated atmosphere, which may have actually carried into the last 20% of the Venus's history and the post-crypto history and the part that's been geologically observed by Magellan. This is really exciting because maybe we can recognize signals of this. It's been published several times by Quaj et al. And others. Next, please. So one point here is that the volcanism, as we know, it's my favorite topic, of course, is really the primary transfer process of volatiles from the mantle to the surface in the interior. So what we decided to do was do an inverse model, okay? So we use the current atmosphere as a baseline and work backward in time. And so we take a look at the nature and magnitude of the major phases of volcanism, shown in one there, the global geological map. We look at the style of volcanism too, because we can see this in the geological data, and the magnitude of volatile output from the eruptions. And then we look at the candidate effects of their volatile release on the observed atmosphere in 3. Next, please. So a key point here is that we try to address a bunch of specific points to sharpen up our ideas about what we need to measure and the kinds of geological and other observations we need to make. So how does the volume of the most recent phase of volcanism, this would be the lobate plains, the large shield volcanoes we've heard a lot about, how does these affect the interpretation that the observed atmospheric CO2 levels, which we've seen are peaked and fluctuate with time in historical times, may be related to current ongoing volcanism? And the second question is, does the eruption of the total volume of the observed extrusive deposits that we see in the geological map and everybody's talked about in the last couple of days, do these contribute significantly to the current atmosphere? And then, of course, the third point, could the period of near global volcanic resurfacing, which spread over 60 to 80% of the surface of Venus, have produced the current atmosphere? So these are the questions that guide us. Next, please. And so we know from volcanism, we know a lot about volcanism. We know how it maps on a bunch of different terrestrial planets and how we can relate it to what's going on Venus. And what do these look like? So clearly, it's very evident that the very high Venus atmosphere pressure, about 93 bars mean pressure, is sufficient to significantly inhibit exsolution of key volatile species during effusive eruptions, shown in one, the work of Gaillard and Scaillet, and Peter Michael gave a really nice talk early on this morning, taking some terrestrial examples. That was actually Monday, taking some terrestrial examples and trying to map those out in terms of speciation and release. Clearly, volatile species are indeed inhibited during effusive eruptions. And indeed, they're altitude dependent. Most of the lavas come out at the lowest levels, at the highest pressures. And The other thing is that they're sufficient to preclude explosive volcanic activity that could deliver exhaled volatiles high into the atmosphere. I'll show in a few minutes, you need about 3 to 5 weight percent volatiles to actually overcome the atmospheric pressure to get explosive eruptions and Plinian types of eruptions. So as I said here, several weight percent higher than typical Earth magmas. And we don't know what the composition is, but that's less likely than likely. Okay, next, please. So what are we trying to do here? We have a global geological record of Venus volcanism. We have a global geological map. This identifies geological units, stratigraphic relationships, and interpretations of the origin of these, like flood basalts or essentially centralized volcanism, et cetera, and we can look at the nature and role of volcanism with time, and then we can estimate the total volume of individual volcanic units as well, based on the stratigraphy, et cetera, and then we can take a look at the time scale. This is a, pardon?
Sorry, I think someone has an open mic.
Okay, thanks. Okay, I was horrified that it might be the time's up sign. Okay, so total volume of individual volcanic units, and then of course we have the McKinnon et al. Time scale. That's the broad scale time scale, but we don't have details of the interior structure of that in terms of subdivision because of the nearly spatially random distribution of impact craters. Next slide. But we can take a look at this geological data, and we've calculated all these different volumes, et cetera, based on the stratigraphy and aerial coverage. And so what we find is that the current high atmospheric pressure really severely inhibits degassing of mantle-derived sulfur and H2O, which is brought to the surface by volcanism and contributed to the atmosphere. Peter Michael gave a nice talk earlier Monday about extrapolating some of the mid-ocean ridge basalts and the speciation there. And again, this is an open question about exactly how this works. The Gaillard and Scaillet work is still good, but you look at it from a different approach. And the question is, if you have a lot more water, that enhances the exsolution of sulfur, et cetera. So this is something that's an ongoing question, but indeed, there's no question that it severely inhibits this, particularly at the lower elevations and high atmospheric pressure. It also completely, severely inhibits Plinian explosive eruptions that can deliver volatiles directly in the atmosphere. Next, please. And the total volume of lava erupted in the stratigraphically youngest period of the observed time is insufficient to account for atmospheric SO2 abundances. So it's highly unlikely that the current recent ongoing volcanism could be maintaining the observed elevated levels of atmospheric SO2. Next, please. Next slide, please. So we can take a look at this from the geological evidence here again for the volumes of these plains. And then next, please. Indeed, these cover 8 to 9%. And we conclude that indeed it's insufficient to really account for recent volcanic activity. Next, please. Okay, so the total volume erupted in the period of global volcanic resurfacing, which is this intervening period here shown by the red arrow. This too it's not so much the CO2 being exhaled, it's the total volume. We've even taken the absolute maximum we can imagine for this from the stratigraphic relationships. This is insufficient to produce CO2 atmosphere that's observed today. So a very significant part of the current CO2 atmosphere must have been inherited from a time prior to the observed geological record, sometime in the first 80% of Venus's history. Next, please. We can see this from looking at these global distribution of the Shield plains. We've estimated the volumes here, and we took the maximum volume for that calculation. Next, please. So again, it must be inherited. Next, please. So the amount of water degassed into the atmosphere during a period of global volcanic resurfacing would have been minimal, even if the atmospheric pressure was only 10% of what it is today. And we don't even know how much water is in the interior as well, but that's the calculation based on what we found here. And the current low atmospheric pressure water content, atmospheric pressure water content may have been an inherent characteristic of the ambient atmosphere and not require enhanced loss rates to space in the last 20% of Venus's history. Next. So finally, the current Venus atmosphere, we would conclude, may be a fossil atmosphere, largely inherited from a previous epoch in Venus's history. And this gets back to some of the modeling we heard by Van Zeiss and others earlier this morning. Very good questions at the end of her talk. If the episodic, this could indeed provide insight into the conditions in the first 80%. And if episodic periods of global volcanic resurfacing built up the fossil atmosphere, even assuming an initial 1 bar atmosphere, more than 90 similar global volcanic resurfacing periods would be required to produce the currently observed CO2 atmosphere. And maybe there were these multiple ellipse-like eruptions here. Richard Ernst and Michael Way have done some calculations on how many would be required. And so that's a really interesting area of research ongoing at the present time. So how do you build up what we think would be a fossil atmosphere? Or could it be inherited from the beginning, as some of the early models predict? The critical outstanding question is, what was the atmospheric pressure, water content, solar insolation tipping point that led to the general stabilization of this fossil atmosphere over the last hundreds of millions of years? This is a really critical question. I would also add that another question is the whole sulfur cycle. We're looking forward to hearing from David Grinspoon and Mark Bullock in a couple of papers here to talk about the sulfur cycle, because this too is poorly known. So all of these things really outline a number of questions. These point to some preliminary conclusions, like we've tried to outline here, that the new data, particularly atmospheric probes and also information from the kinds of weathering processes, which are critically important, and Marty Gilmore talked about any kind of landing assessments of what's going on and better understanding of how the atmosphere and the surface interact and how the interior degassing is related to that. This is just a very exciting time for upcoming armada of Venus missions. Thank you very much.